Hello and welcome back to Calculus. First, I'd like to thank all the nice people that support this channel by liking and subscribing. It means a lot and helps me make more math videos for you to enjoy. Today's video is going to be a continuation of the last video about integration by substitution. Please recall that we use this when integrating complex composite functions. We first set our u as the so-called inside function, in this case gx. Then we have to compute the derivative of u so that we can replace dx with du. And then our integral is going to become the following. We'll be integrating f of u du, and our new variable is going to be u. After that, we compute the integrals, and finally plug the substitution back into the antiderivative function for the final answer. I can tell you that this, however, was the basic theory of integration by substitution. Now, I'd like to go over more complex substitutions, to be precise, trigonometric ones. However, before we get there, I'd like to first show you an example with a weird substitution trick which may be useful. Suppose we're tasked with evaluating the integral of x times the square root of x plus 1. In this case, we use the substitution u is equal to x plus 1. And then you compute the derivative of u. So du dx is going to be equal to just 1. So that basically means that du is actually equal to dx. So now our integral is going to become the following. It's going to be the integral of x, the square root of u, du. However, here we encounter a problem. We have already transformed our integral into an integral with respect to the variable u. However, we still have a variable x here, and there's nothing we can do with it. Only the funny thing is, there is something we can do about it. Because we said in our substitution that u is equal to x plus 1. So if I slightly rearrange this, to be precise, move the plus 1 from the right-hand side to the left-hand side, what I get is u minus 1 is going to be equal to x. So now, that means that in the integral, instead of x, I can just write u minus 1, and then times u to the power of 1/2. After that, I can open the parentheses, and I would get that it's going to be u to the power of 3/2 minus u to the power of 1/2 du. And this integral can be integrated easily with the power rule. I will not go into detail about how I got this, since you already should be fluent with the power rule. And finally, of course, we just have to plug our substitution back into the antiderivative function. And this right here would be our final answer. So please keep this trick in mind. Remember, the most important step that we did here is this. When we did the substitution and then we rearranged it in order to compensate for the other x that was singled out. All right, so now that we got this out of the way, let's talk about trigonometric substitutions and why exactly they are useful. So the golden question here is going to be, when exactly do we even use the trig substitution? Well, these bad boys are right here. The functions that have radicals in this format are difficult to integrate directly or with casual substitution. Thus, we need to employ trigonometric substitution, sine, cosine, and tangent, in order to simplify the radicals. The theory behind this is that we use the trigonometric identity, and there are actually two of them. More precisely, they are called the Pythagorean identities. These two Pythagorean identities are something that you definitely should have learned in trigonometry, and I also mentioned them in the introduction video. So now the golden question is, for each of these formats, what substitution do we use? Well, for square root of a squared minus x squared, we will always use x is going to be equal to a sine of u. For square root of x squared minus a squared, we'll always use x equals to a secant of u. And finally, for x squared plus a squared, we will always use x equals to a tangent of u. I would definitely and highly recommend you to remember this table. If this seems extremely confusing, for now, I can tell you that it definitely is. So, we are going to take a look at an example. Let's say we have to integrate the function 1 over the square root of 9 minus 4x squared. Please immediately see that our function here matches the first case in the table. Immediately we'll know that we'll use a substitution x equals to a sine of u. Of course, firstly, we do need to figure out what a is. Well, a squared in this case is 9, so that means that a is going to be equal to 3. But if you said this, that wouldn't be really correct. Because a must-have thing here is that the coefficient of x squared must be 1. Or in another case, there should be no coefficient, just minus x squared. So what do we need to do here? We need to first divide the inside function by 4. Well, to be more precise, we actually took the 4 outside of the parentheses. Thus, in the parentheses, we got 9 over 4 minus x squared. Now, 9 over 4 minus x squared actually is going to satisfy the condition to use the trigonometric substitution a sine u. Of course, only here at the bottom, we can first simplify the 4, because we can actually rewrite this as 2 separate roots multiplied together, and then take out the square root of 4, which is simply 2. Now, our a squared is 9 over 4, so that means a is going to be equal to 3 over 2. And then the substitution that we can use is x equals to a, so 3 over 2, sine of u. Please note here, I simply took out the 1/2 in front of the integral because it is just a coefficient. In the bottom, I plugged in my substitution and I get square root of 9 over 4 minus 3 over 2 sine u squared. Now I can actually open the parentheses here. However, here we encounter a problem because, as you can see, we don't have the dx, or in another case, the du. So the question is, where the hell did it go? We need to differentiate our substitution right here. Only this time, it's not going to be du dx, it's actually going to be dx du. And this is going to be 3 over 2 cosine of u. In other words, dx is going to be equal to 3 over 2 cosine of u times du. And that is exactly what we are going to write here instead of dx. 3 over 2 cosine of u du. All right. Now next up, I'm going to do several things at the same time. First, I'm going to factor 9 over 4 to the outside and take the square root of it. I'm also going to combine 3 over 2 with 1/2, since they are both simply coefficients. Now here, finally, at this stage, I can actually start simplifying things. Well, first of all, step number 1, here in the bottom, we have a 3 over 2. That is the same thing as times 2 over 3, so it means we can simplify it with the coefficient in front, 3 over 4. What you get is simply going to be 1/2. Then, under the square root, we can finally employ the Pythagorean identity. Sine squared x plus cosine squared x equals to 1. So 1 minus sine squared x is going to be equal to cosine squared x. So that means here under the root, what we're going to get is the square root of cosine squared u, and we know that this is just cosine of u. And then in the end, it's also multiplied by cosine of u du. So what exactly happens here? Cosine of u can simply be cancelled out. This means our integral can be simplified to 1/2 integral of just du. And we know that this is basically like integrating the number 1, and what you're going to get is 1/2 of u plus c. However, we're not done, because we were supposed to find an antiderivative function with variable x. But now what we got is an antiderivative function with the variable u. But also, in the substitution, we used x is equal to 3/2 sine u, which means we haven't got an explicit expression of u in terms of x. So that means we need to get it ourselves. And step number 1 would be to go back to our substitution x equals to 3/2 sine of u. Step number 1 here will be to move the 3/2 to the other side. So what you get is 2/3x is going to be equal to sine of u. And those of you who know trigonometry very well, you probably already know here we can use the inverse sine function in order to express u explicitly in terms of x. So u is going to be equal to the arcsine function of 2/3x. So then finally, we can actually plug this into our antiderivative function expressed in terms of u, and the answer you're going to get is arcsine of 2/3x divided by 2 plus c. And this right here, ladies and gentlemen, is going to be the final answer to our integral 1 minus the square root of 9 minus 4x squared. You are probably thinking at this point that this is a lot to digest, and you would be right. Now, since we used the substitution x equals to a sine u already, I will put 2 exercises that use a secant of u and a tangent of u for you to try out. And if you want to check whether you did it correctly, check the link in the description for the PDF version of this lesson, where I will provide the step-by-step solution for both of them. If you want the PDF version of previous lessons, they have all been linked in the description of the corresponding videos that I've posted before, and they are available for you to save and download for free. In the next video, we are going to take a look at how to evaluate definite integrals with substitution, where I'm going to show you a little trick that you can use regarding the bounds of the integral. So I really hope to see you there, and have a nice day. Bye!